We do all agree that using electricity from fossil fuel sources is outdated. And we need to get this energy from renewable energy sources. And among these sources, solar energy stands out because of its global character. More than enough solar energy is hitting the Earth every day to power it many times over. But one of the big hurdles is where to put it. In places where we most need energy, there isn't a lot of space to put big, heavy, opaque solar panels. Of course, if we can make these thin, lightweight and transparent, we can put them almost everywhere. And organic solar cells, like this one, do possess all of these properties. An organic solar cell consists of an active layer sandwiched between two electrodes. The active layer is a blend of a donor and acceptor material, resulting in a bulk heterojunction model. When a photon strikes the active layer, an exciton is produced. Afterwards, charge separation occurs at the donor-acceptor interface, leaving a hole in the donor and an electron in the acceptor material. These opposite charges then travel to opposite electrodes, and a current is created when they recombine via an external circuit. To get the efficiency of the solar cell as high as possible, it needs to absorb as much photons as possible. Therefore, most solar cells absorb in the visible region of the solar spectrum. But this means that your device appears non-transparent. In an organic solar cell, however, the absorption can be tuned so that photons of the visible light can pass through, while the device absorbs photons in the near-infrared region to create energy. In this way, the device appears transparent, but electricity can still be generated from the energy from the infrared region. Now, to shift the absorption of the solar cell to the near-infrared, the push-pull material approach can be used. The state-of-the-art electron donor material used in a bulk heterojunction organic solar cell is a donor-acceptor type conjugated polymer. A more electron-rich and a more electron-deficient heteroaromatic moiety are combined in an alternating fashion over the polymer backbone. By tuning the strength of this push-pull interaction, the absorption can be tuned. A stronger donor combined with a stronger acceptor will result in a decrease of the band gap and therefore a redshift of the absorption. So, if the donor and the acceptor are strong enough, the absorption can be shifted to the near-infrared region. In my PhD project, I focus on the synthesis of these push-pull type conjugated polymers that absorb in the near-infrared. Via still reaction, I can polymerize a stanulated donor and a brominated acceptor. In this example, a dithienoparole and diketoparole were coupled and purified via Saxelin extraction. Structural properties of the final polymer were determined via Malditov spectrometry, and the final polymer was evaluated on molecular weight via high-temperature gel permeation chromatography and on absorption profile via UV-vis spectroscopy. Afterwards, this material can be combined with a commercial small molecule acceptor in the bulk heterojunction layer of the lab-scale solar cell device. I so far reached an efficiency of 1.44% with an average transmission of 34% in the visible area. Of course, with room for improvement. Several other materials are also being synthesized and analyzed for this application. But the greatest challenge is still to find a suitable combination of donor and acceptor material to reach optimal offset between energy levels and an ideal morphology in the bulk heterojunction blend. Now, take a last close look at this organic solar cell, because chances are in a couple of years you won't be able to see them anymore.